Okay, so maybe that previous video, the example was not perhaps as silly as I suggested. So what I want us to think about now, okay, we've got the analogy of the year 13 student falling into that well. By the way, the word well is used very deliberately there. We call it a potential well. Remember, when something is held, joined or bound to something else, you need energy in order to separate it, to free it. That concept is described in physics as having negative potential energy. You've fallen into a potential well. You need to get that energy back to zero in order to escape. Back to zero minimum. Zero is the minimum, and then any extra energy you've got can take you away. So what we find is this, okay, the photoelectric effect. I'm just going to call it PE, okay, the photoelectric effect. Basically, what happens is, okay, it says this. It says that when light is shone on a metal, electrons escape. So what we're saying here is that the electrons themselves are here, and the electron is in a, oops, just disappeared, that is in a potential well. In other words, instead of that year 13 student being at the bottom of this well, we've now got an electron. Now, of course, it doesn't mean physically that they're physically lower down or anything like that. We're just describing the energy state that they have. Now, last time we said that the person had fallen down a height h and they needed energy mgh to escape. They needed that minimum to escape. What we're going to do now is we're going to say that the electron is held, and the amount of energy that it's held with, the amount of negative energy that it has, if you like, is going to be called, we're going to give it a strange name, admittedly, it's called the work function, and it's given the symbol phi, like that. Okay, so the energy we need to release this electron has to be at least the work function. So if the work function is 1 joule, we're going to need at least 1 joule to get it out there, maybe some more joules to give it the extra kinetic energy on its way. Now, instead of just a mysterious packet of energy flying through, this packet of energy has got a name. This packet of energy that I was talking about before is called a photon. So a photon is, as you might already know, a light particle. So don't worry about light being a wave just yet, okay? In this model, we have to think of light as being a particle. In fact, the only way this whole thing works is if we assume that light is a particle. We'll get into that later. A photon is a light particle. You might just want to call it instead a packet of energy. So let's just look at some scenarios now. Let's say here is our photon. So this is our emergency energy now, as we described it last time. Here's a photon, and let's say its energy is less than the work function. Now, the photon goes in like this. Well, if it's less than the work function, nah, it's not going to do anything, is it? The electron that's held here will go up a little bit, but won't be able to break free. What about though? What about if instead we have another packet of energy here? I'm using these colours quite deliberately. They don't mean anything very specific, the exact calculations, but maybe you get a feel where I'm going with this. Just see. So let's imagine we get another packet of energy, another photon. But this photon, let's imagine the energy is exactly equal to that work function. So it goes in like this, and yes, guess what? That electron will be free. Okay, it won't have any kinetic energy by the when it gets free, but we can trust that it will be able to be freed. Right, so what about then if we have another packet of energy, another photon, another particle of light? All right, but this time the energy is bigger than the work function. Well, in this case, look, the energy will go in here. It's more than the work function, which means our electron can not just escape, but once it escapes, it will have some extra energy. It will have some kinetic energy as well. Can you see what I'm getting at here? It's the same thing as that person trapped in the well before. It's exactly the same idea, but we're talking about a well in a metaphorical sense now. We're saying that the electron is trapped, i.e. it's bound to this metal. If the packet of energy, the light that we shine at it, has not enough energy, it will not be freed. If it has just enough energy, it can just about be free. If we give it more than is needed, it will not only be free, but it will have some kinetic energy once it's escaped as well. Photons are particles of light. And interestingly enough, what we can say about a photon is this. The energy of an individual photon is given by this equation. Energy in joules equals Planck's constant is what H is. You'll find that in the data booklet. After a while, you'll get familiar with that. Planck's constant. And F is going to be the frequency of the light, obviously relating to its colour. Now, another way to write this is energy of a photon equals hc over lambda. Well, we know from the wave equation, don't we, that the speed of a wave equals frequency times wavelength. So instead of writing frequency, some people just write c over lambda here. Whichever way you want to do it, okay? I prefer using hf. It just seems to, I don't know, it just seems to fit better somehow. So look what we could say in each of these scenarios here. Instead of saying the energy was less than phi, I could have said hf was less than phi. Here, in the next one, I could have said hf equals phi. In the other one here, I could have quite easily said hf is greater than phi. So the energy of that packet, the energy of the photon is hf. If it's bigger than phi, great, the electron is released and it's got some spare kinetic energy. If it's just about equal to phi, just about frees it. If it's less than phi, forget it, you're just wasting your time. Now look at this, isn't it interesting that H is common to all of these? So the frequency is the thing that differs. You know, the HF is less than phi, equal to phi, greater than phi. The frequency is what differs. That means there is a cut-off frequency when we can free the electron. Below that frequency, we end up with HF being less than phi, we cannot do it. At that frequency, we've got HF is phi. Greater than that frequency, it's greater than phi, so it can happen. So the cut-off scenario between us being able to free an electron and being able to not free the electron, just wasting our time, is going to be this scenario here. So if the energy of the photon is just equal to the work function, then that's kind of the cut-off frequency. We call it the threshold frequency, the threshold over which the electron can be free.